This is Mahdi Geraylu, postdoc researcher from University of Tehran. I recently joined to the Tallinn University of Technology. This presentation concentrates upon the ACPA method in which approximate computing is being employed in the imprecision optimization of fixed-point LTI system. So firstly, I talk about importance and necessity, some preliminaries, then our contribution in imprecision optimization flow, and finally the presented method in details. The importance and necessity of imprecision optimization actually come from the fact that computation in hardware are not exact. Every multiply or add dramatically needs the precision increase to represent the ideal result as shown. If the operation are performed successively without precision reduction, the processing due to the hardware growth rapidly become impractical. And finally, in error-resilient application, the inherent error resiliency can be exploited to achieve energy efficiency. The quantization is memoryless, deterministic, and nonlinear operation. This operation converts input to represent any of the input values within a range of input plus minus delta over 2, where delta is quantization step. There are 4 types of quantization. They each introduce error for different reasons, and they require a different kind of analysis, including overflow, input quantization, product quantization, and coefficient quantization. Since nonlinear analysis is complicated, it is more practical to handle quantization by modeling the quantization process as a linear process. So it is treated as the addition of an error signal and is approximated as a uniform white noise signal. The white noise is uniformly distributed on the range of quantization step, uncorrelated with input, and a zero mean as well as a stationary process. The precision optimization phase is a highlight optimization that comes after decomposition and factorization and before synthesis in design flow. In the phase, some bits in integer and fractional parts are discarded for hardware reduction, such that no overflow occurs and the computational results would be accurate enough. Our contribution is proposing a precision analysis flow in which the proposed path replaces the classical path. The current precision optimization flow starts off extracting the area and quantization error models. Then the optimum FPs are obtained through the iterative process in classical path. The classical paths mostly suffer from some weaknesses of wasting error budget and long runtime. In the proposed path, the FPs are obtained through 2 phases, FP optimization and exploiting approximate computing. In the first phase, the optimum FPs are assigned using the Lagrange multiplier method with linear computational complexity in continuous space. In the second phase, the inherent precision analysis weakness is addressed. This restriction causes the precision analysis-based methods not to consider the entire error budget tolerable by a given application. To alleviate it, we employ the approximate computing technique as a complementary, utilizing the remaining unusable error further to more hardware cost saving. In our presented FP optimization, we divide the error budget among the variables, which is called the error portion, based on the area impact In this way, more effective variables on the area get lower FPs, which leads to hardware cost reduction in the allowable error budget. Since in the LTI system, the area is modeled as a linear function, the area effect is extractable from the variable slope in the linear area model, as we see. The fees are then assigned based on the portion from the intersection of error model and error portion. By using the Lagrange multiplier method, it is proved that the fee assignment is optimum in the continuous space and enjoy a linear computational complexity. Let's look at the yellow rectangle. Converting the continuous solution to discrete ones often leads to some error space, which is mostly wasted in previous works. We tried to use the error budget by approximate computing. For explaining the basic idea, let's consider word length optimization as a kind of approximate computing with the diagonal truncation. So in the higher bit, it produces an error with the order of the MSB or error order 1. Another AC technique can be considered vertical truncation, generates an error with the order equivalent to the LSB, or error order 2, which is less than error order 1. So the basic idea is the remain error, which is unusable in the fee assignment, can be utilized through the AC phase or vertical truncation. Let's consider we have a portion of 100. So the remaining error is 22 10,000ths, which is unusable by word length optimization. In this case, the vertical truncation provides the possibility of discarding 6 units in the multiplier. By such the saving, we encourage to expand the error budget more for vertical truncation instead of diagonal truncation through the precision increase. So in the second figure, the multiplicand FP is increased by 1 bit. The VT in this case provides 8-bit unit area saving. In the third figure, a 2-bit increase leads to a 7-bit saving, which is less than the previous one. So the increase don't always cause more area saving. The reason is approaching the vertical truncation error to MSB produce the error equivalent to the diagonal error. So there is an optimum breakpoint for the vertical and the diagonal truncation. To obtain the point, we have modeled the approximate area and error. Then a two-variable optimization is applied to determine the point. So in this slide, we model the approximate error and area model for adder and multipliers. For area model, the array multiplier is considered the parallelogram composed of partial product bits or units of 1 bit. In the approximate area model, the effect of the x bit increase in the first operand and the vertical truncation of from the curve LSB in the right triangle is considered. So the area of triangle, which is k times k plus 1 over 2, should be subtracted from the parallelogram area. For error model, the array multiplier use k-bit vertical LSB truncation in the right triangle, and its multiplier is a fixed point constant. The error space required for the truncation is provided by remaining error of the first phase plus an x-bit increase in the. In this case, the error model is the summation of quantization error, the discarded carries plus the discarded value of the MSB. The real error for 10,000 uniform random values assigned to the non-constant operand is compared with the maximum error obtained by the approximate error model. As seen, the maximum error in the histogram are equal to the mm obtained by the approximate error model. The arithmetic units are replaced with the approximate ones to use the remaining error budget. The ACPA has been compared with the state-of-the-art methods applying to the benchmark. The results show that our method can improve the area by about 20% and delay by about 9% on average compared to the state-of-the-art methods. This is reference. Thank you.